Hi everyone, and welcome to the final lecture of this week's module. This lecture is going to start our exploration of experimental design material. We'll get into the bulk of that material in the following module, but first I want to tackle the concept of causation. Causation means that when one variable changes, another variable changes as well. In research methods, the independent variable will cause a change in the dependent variable in some manner. Causation is the primary goal of most explanatory studies. Researchers looking to explain crime, for instance, are searching for that one independent variable that will create change in the crime variable so as to better understand how to reduce crime overall. The problem is that causation is a difficult determination. Causation statements require three major things: temporal ordering, association, and non-spurious relationships. Let's discuss what those terms mean in more depth. Temporal ordering means simply that cause comes first, which makes sense, right? If the independent variable is influencing a change in the dependent variable, then it needs to come first in time. Its presence will then initiate a change in the dependent variable as expected. Now, temporal ordering sounds like an easy concept to determine, but it's actually a lot more difficult than you think. For example, in criminology, there's a large debate over the roles of genetics versus socialization. Were you born with a criminal gene, or were you socialized to become a criminal? I'm simplifying this debate here, but you get the point. The problem is the time ordering issue. How do we disentangle the social aspects of your childhood with your own genetic material? The ability of a research study to prove temporal order exists is highly dependent on the time dimension of the study. There are two main time dimensions: cross-sectional and longitudinal. A cross-sectional design means that data is only collected from the research subject at one point in time. You take a survey, you hand it in, and you're done. On the image here, you can see this cross-sectional design indicated as occurring only at T1, which stands for time 1. Longitudinal designs, on the other hand, take place at two or more times, meaning that you collect data from the research subject at least two separate times, and many times more than two. Longitudinal data is key to proving temporal order. If you only collect information at one point in time, you'll only be able to observe both the cause and the effect together. By spacing out your data collection periods across multiple time points, then you can observe the cause first, identify that the effect is not present, and then later determine that both cause and effect are present, thereby proving temporal order. There are three common subtypes of longitudinal designs: panel, cohort, and trend. Please note that these subtypes are not discussed in your textbook, but they are important terminology for you to know. So what is a panel study? A panel study means that you gather data from the exact same research subjects each time you collect data. So we start with our research plan. We're going to collect data at time 1 and time 2. At time 1, we gather 5 people. When we get to time 2, whenever that is, we need to gather the exact same 5 people again and collect more data from them. The time period between time 1 and time 2 doesn't matter. It could be an hour, a day, a week, a year, even a decade. The important thing about a panel study is that we keep the same people. Now, panel studies are the best option for proving temporal order because they allow us to document the exact time that cause and effect both presented themselves with each individual research subject. So if subject 1 was smoking at time 1 but was healthy otherwise, and then at time 2 was still smoking and now has cancer, we can document that smoking came first and cancer came second. However, because panel studies keep the exact same people each time, this can make the research study much more difficult to complete. What if person 4 dies before we collect data at time 2? Now we're left with 5 time 1 observations, but only 4 time 2 observations. This dropping out is called attrition. Attrition rates in panel studies are the highest of all 3 longitudinal studies because we rely on the exact same people. Attrition can be caused by people dying, like in my example, or it could be people that opt out of data collection, or people that get lost and the researchers can't find them. The longer the time between time 1 and time 2, the higher the attrition rate you'll have because of these issues. Attrition rate concerns are why researchers will often utilize a cohort approach to longitudinal studies. In cohort studies, the researchers gather a group of people with similar characteristics each time, but they don't have to be the exact same people. For example, birth cohorts are a very common research approach. At time 1, researcher will gather data from 5 people that were born in a specific year, say 1980. At time 2, the researcher will find 5 more people born in 1980. Because the researcher doesn't have to find the exact same 5 that they interviewed originally, attrition is much lower. But now the temporal ordering is more suspect. Just because subject 5 was a healthy smoker at time 1 and subject 5 was a smoker with cancer at time 2 doesn't mean the same as a panel, because subject 5 is now a different person. Maybe the subject at one time got cancer first and then started smoking. Who's to say that the temporal ordering existed the way we actually thought? So cohort studies are good for attrition rates, but they're more problematic in terms of temporal order determination. The final type of longitudinal design is a little different. This type of design, called a trend study, doesn't look at individual people whatsoever. Trend studies look at populations over time. Because of this definitional difference, trend studies often study at least 3 or more time periods, and they commonly include very long time frames, longer than most normal panel and cohort studies. Because trend studies are looking at the population as a whole, the data collected at each time period will be some form of rate or percentage, with the goal of showing the change over time. For example, here are hypothetical rates that were collected at 7 different points in time. Researchers can graph and compare these rates to determine how the event is changing in the population, but they don't know anything about specific people or specific cohorts within the data. This is just an overall rate about the entire population. Shown here is a graph from the Center for Disease Control that illustrates the rate of violent deaths caused by firearms. The data is broken up into 4 categories: the blue line representing Black persons, the green line representing white people, the purple representing American Indian people, and the light yellow representing Asian and Pacific Islanders. The rates of gun violence fatalities in all 4 ethnic groups is graphed, starting with the rates in 2001 and ending with rates in 2018. Like cohort studies, trend studies are not as good as providing temporal order because you're not looking at individual people in the population. However, trend data can be very useful in documenting overall trends to see how events are changing within a single country over time. In case you didn't know, the CDC actually has multiple online databases that allow you to analyze trend data in the United States for free. The website here that I've linked gives you the CDC Wonders website, which actually links you to a whole bunch of different web databases that you can use. To get this graph, I used the link provided under cause of death, which took me to the Fatal Injury and Violence database, where I could easily make all of these graphs and tables quickly. This website might be of interest to you, some of you, in future papers or for research projects. Okay, so now that you understand the requirements for temporal ordering, let's talk about the second requirement for causation, association. Association means there is a statistical association between the independent and the dependent variable. This can be linear or curvilinear associations. In linear associations, as the cause increases, so does the effect. As the cause decreases, so does the effect. This is shown in graphs 1 or graph 2, with the x-axis representing the cause and the y-axis representing the effect. Curvilinear relationships, on the other hand, mean that there's a change in the relationship at some point. In graph 3, you can see that at first, the cause and effect both increase, but then as the cause continues to increase, the effect starts going down. In graph 4, the magnitude of the effect increases as the cause gets bigger. Now here is my warning on this. A statistical association is the easiest requirement of causation to achieve. Statistically, with large enough samples, we can find associations between pretty much anything that we want. So you need to be aware of this as a critical consumer, because researchers may find a statistical relationship and then conclude their research proves a cause and effect relationship, even though they haven't proven the other 2 requirements of temporal order and non-spurious relationships. And that brings us to our last requirement for causation. I do want to warn you that this requirement is the one that is least likely to be met because it is simply so difficult to do in social science. The last requirement is non-spuriousness, which is a little confusing because when I say we want a non-spurious relationship, what we're actually talking about getting rid of is all the spurious relationships. A spurious relationship is a false association between two variables that's caused by a presence of a third variable. Simply put, a spurious relationship makes us think there is a statistical relationship where there actually isn't. Your textbook describes two types of spurious relationships. Confounding factors are those that influence both the independent variable and the dependent variable. So you may see a change in the IV and the DV at the same time, but it's not actually caused by another variable, or it's actually caused by another variable. It's not caused by a cause and effect relationship between the two. Here's an example of a confounding relationship. I'm trying to explain what causes a person's math skill to increase. I collect data from my subjects, and I find that as shoe size increases, math skill increases. Statistically, these two variables are related, but common sense tells me that something else is going on. So what is it? To find a confounding relationship, we need to think about the variables that would influence the independent and the dependent variables separately. So what variables can you think that would change a person's shoe size and a person's math skill independently? Age, right? As a person gets older, their shoe size increases. As a person gets older, their math skills increase. When I include age in my statistical analysis as a control variable, then I find that the statistical relationship between shoe size and math skill doesn't exist. This alerts me to the fact that the original relationship was a spurious one that was caused by the confounding variable of age. The other type of spurious relationship that your textbook describes is that of an intervening variable, which is also called a mediating variable. A mediating variable changes the relationship between the independent and the dependent variable. In some cases, it can completely erase it, while in other cases, it may simply reduce the magnitude of that effect. Here's an example. I'm doing a research study and I find, statistically, that a student's grades will increase their happiness. However, I read over other research and I find that other researchers have noted that a person's self-esteem will also influence their overall happiness. So I add self-esteem into my statistical models. I find that as higher grades still increase happiness, but those students with higher self-esteem will have a higher level of happiness from the same grades as their peers with lower self-esteem. So self-esteem is serving as a mediating or an intervening variable. It isn't erasing the cause and effect relationship between grades and happiness, but it is changing it. We depict this with a perpendicular arrow like I did on this slide. So how do I prove non-spuriousness? In order to prove that a relationship is not spurious, you have to measure and account for all possible intervening and confounding variables. That means that you have to consider every other possible cause in your analysis in order to determine whether or not the statistical relationship is non-spurious. As you can imagine, this is a momentous task. Think of all the variables that could influence your happiness. Your self-esteem, your grades, your parenting, your financial stability, your housing situation, your social interactions. The list goes on and on. I won't say that proving a non-spurious relationship is impossible, but it is certainly not easy. So what does all this mean for you as a critical consumer? Well, first of all, cross-sectional methodologies are inherently unsuitable for proving a cause and effect relationship. And researchers studying a complex concept like happiness or crime will likely be unable to prove beyond a doubt a non-spurious relationship. The only thing that is easy is the statistical association. So remember, don't take statistical association as proof. That's why we have that famous adage that you may have heard before. Correlation does not equal causation. Just because statistically there is a relationship doesn't mean there is a real cause and effect situation occurring. So conclude wisely. The best way to prove causation is to use an experimental design. This allows you to utilize specific time dimension and experimental controls to try to ensure the best research conclusion possible. In the next module, we'll start exploring those different categories of experimental designs. Until then, thanks for watching, everyone.